Our speaker today is Tabaré Roland, and his title, as you can see there, is the L1 cross product associated to a topological dynamical system. Please, Roland, Tabaré, go ahead.
Thank you. Thank you for inviting me to speak here. And before starting, I would just briefly say something that this work was done under the supervision of Matilde Martinez and Fernando Adi. And I want to particularly mention this because Fernando sadly passed away at the end of last year. And well, none of this work would have been possible without him. So I just wanted to say that. So let me start with the talk. So as you see, I want to talk about some kind of cross-product construction. So first, let me state the setting in which we will be working. So our setting here is we have Xi, a countable infinite discrete group. We have X, a compact and Hausdorff space, compact Hausdorff space, and we have an action Xi of Xi on X via homomorphisms. I really know this action by sigma. So basically what we have here is for every element of the group, we have a homomorphism sigma sub s from X to X only. So this action is the same as giving an action of Xi over the continuous functions on X. So here C of X denotes the continuous functions from X to the complex numbers. F is continuous. And the action is given, I will know this action by alpha. This action is given basically this way. If I have an element S on the group, I have a map alpha sub S from C of X to C of X that is given by when I evaluate this on a function and then I evaluate this on a point, this is F on sigma S to the minus 1 of X for every F in C of X and for every point on the space. So basically, I can translate the action of the group on the space as an action of the group on the continuous functions on this same space. So the idea is I wanted to construct an algebra that, in some sense, the operations of the algebra encode the action of the group of the space. So what I will do first is I will consider this space that I will denote like this, that basically consists of the functions from Xi to the continuous functions on X, such that the continuous function I choose for almost all elements of the group is 0, except for a finite number of elements of the group, except for a finite number of S in Xi. So basically, what is me here is, well, for a finite, I choose finite elements of the group. For those finite elements, I can choose a function. And then for all of the other elements, I choose the 0 function. So you can endow this space with an algebra structure. So well, first let me say something. I will given an element here. Let's say I have F in this space. I will use this notation. I will write F as the sum over the element of the group of F of S delta S. What does this mean? Basically, what I mean is for every element of the group, I have to pick a function. So I write this here. And this sum makes sense in the sense that only a finite number of these summands are non-zero. And also, I will write this sum as this F sub S delta S. So basically here, what I'm doing is I'm defining F sub S as F of S. So basically, you can think of this as, well, I'm choosing a finite functions, and for every function, for every of these function, I associate an element of the group. So now with this, I can define a product in this space, product. Basically, what I have to say is for every let me write like this. If I choose two elements of the group, S and T, and I pick two functions, f sub s, f sub t on X, is it enough for me to define how the product is given is on these elementary elements? So what do I mean? What do I mean by this? I mean this is the element from here that maps S to this function and every other element of the group to the zero function, and the same with this element, but only with I'm choosing the another element of the group. So the product between these two elements is f sub s alpha s of f sub t delta st. So basically, what I get is that this element acts on this one. I move to this fiber, and I get this product, essentially. And then if I define the product in this element, then by linearity, I can simply define it in every other element of the space. So I will also define an involution in this space that basically is defined like this. If I choose an element of the group and I choose a continuous function, then the involution on this element is simply alpha s to the minus 1 f sub s conjugated delta s to the minus 1. So basically, I recall what does this mean? This means that for s, I'm picking this function, and for every other element of the group, I'm picking the zero function. So when I do the involution of this element, what I get is a function. What I get is a function that's given that in s to the minus 1, the value is this other continuous function, and in any other element of the group is 0. So if there is any question, please interrupt me. So the other thing I want to comment is that you can canonically C of x, the continuous function on x, is canonically contained in this algebra, because simply what I have to do is, if I take an element in C of x, I identify it with the element f delta s that belongs to this space, where, just in case, let me clarify, E is the unit in is the identity element on the group. So basically, if I have a continuous function of x, then I can see this as in this space simply by saying, well, I take the element that in the identity of the group takes value f, and in every other element of the group it takes value 0, right? So the thing is, when you define this structure, essentially here you have this that I said before, that the operations of the algebra kind of codify the action of the group on the space, because if you compute this, if you compute even an element of the group and a continuous function of x, you have that delta s f delta s to the minus 1, this will be equal to alpha s of s f. So basically, when you compute this, you get that s acts on f. So essentially, what you have here is that the operation, the product of the group essentially codifies the action in this sort of sense. So the thing is, this is an algebraic structure. It has only an algebraic structure. So I want to endow it with a norm and take the completion with respect to that norm, so I can get an analytic structure of some sort, right? So here I have to pick I have to make a choice to pick a norm. I said, well, I take the completion with respect to this norm, and what I obtain will be a cross product that has the type of norm I have chosen. So here, let me write it. what I mean is, I want to endow this algebra with a norm in order to obtain an analytic structure. So the thing here is you have many choices to do. Like, for example, you could choose, for example, let's say a C-star norm. And then usually you have two obvious choices that are the universal norm and the reduced norm. And then if you know this space with, for example, the universal norm, and you take the completion, what you get is the universal cross product associated to the action that usually is denoted like this. You get, well, usually this is the notation you use. You get the universal cross product of C-star cross product in this case, because I'm putting a C-star norm associated to the action. And if you put the reduced norm, you get what is called the reduced cross product associated to the action, that usually is denoted like this. And obviously what you get is C-star action. But you can pick other choices. For example, another choice will be, let's say, an LP operator algebra norm. Again, here you have two canonical choices that are the reduced and the universal norm, and you get the corresponding cross product. And so essentially what I mean to say here is that you can choose a norm, and the norm you choose will define the structure you get. But the thing is, there is reason to expect that you might lose information when passing from this algebraic structure to the completion. And there are reasons to believe that some norms, some choices you might do, might retain more information of the action you started from than others. So the one I will study, so this one I will actually define. The one I would like to work with is some kind of L1 norm that is defined this way. So let's say that I take an element from the algebraic skeleton of the algebra. I think, sorry. Sorry. I will define the norm of this element as the sum of the supremum norm of F to S for every S on the group. And just in case, let me say that the supremum norm is defined as the supremum over all elements of the space of f of x. So this is well defined because this sum is finite, so everything's all right. And what I will define is the L1 cross product associated to the action simply as the completion of this algebra we started with. We take the completion with respect to this norm I have just defined. Yeah, so this is the definition of the algebra, and actually this has a quite concrete description. Simply the elements f that you can write as a sum of f sub s delta s, such that the series, the norm, the sum of all of these norms converge. So the difference essentially is that in this algebra I started with this one. I had only finite elements that were non-zero. Here I can have infinite elements that are non-zero, but this sum must converge, right? But it's quite.
Sorry, just
yes.
a question. This is different from F1 of G, right? Of G.
Yeah. Sorry, I should have said that. Yes, actually, this is different because the if one of these is what you do is you put it inside an L1 space, inside the operators of an L1 space, and then you take the completion there. But this is you will get something different than this. It's different indeed. So essentially, this is kind of when you take the L1 algebra of a group, it's the same idea. Because here you have, what you have is essentially the hard measure on the group, that is the continuum measure in this case, because the group is discrete. And you work with that. But for example, the F1 algebra of the group, like the L1 operator algebra of the group, it's different than the L1 algebra of the group in the sense of harmonic analysis. Yes?
And this is closed under convolution.
Yeah, exactly. Yeah. Yeah, exactly. This I didn't write it, but this product is like the convolution, essentially. Yeah, it's essentially that you're using that as an inspiration. And actually, let me write something. Example: if you have the action, the trivial action of she on a point, then the L1 algebra of she acting on the point is exactly the L1 algebra of the group. So you are covering the algebra of the one algebra associated to a group. Any more questions?
So the top
Yeah.
concerns groupoids that arise from group actions on spaces.
No, actually, this is
or more general groupoids.
This algebra is not a groupoid algebra. That's something you can use to distinguish this one from the F1 operator algebra to the L1 operator algebra, because that one is basically the information you use to construct that algebra is the transformation groupoid of the action. So essentially, I will go into that later, but essentially it depends on the orbit equivalence of the action. Whereas this one is not a groupoid algebra. You could have two groups that have the same transformation groupoids, two actions that have the same transformation groupoid, that they do not give you the same L1 algebra. I will go into that later.
Okay, thanks.
So, well, I said that you had this algebraic skeleton. You had many norms you could put here. The C-star norm, for example, usually is the one that has been studied the most for the longest. But recently, for example, the LP operator algebra has been also studied a lot. So, is there any reason to choose this norm instead of the other ones I have done? So, I want to mention two precedents that are interesting. And the first one is called Wendell's theorem. Wendell's theorem. So essentially, it says that if you have she and H, two topological groups, such that the L1 algebras they give are isometrically isomorphic. L1 of she and L1 of H are isometrically isomorphic. And then she and H are actually isomorphic as topological groups. Are isomorphic as topological groups. So what does this mean? It's clear that if you have two groups, G and H, such that they are isomorphic as topological groups, the algebras associated to them must also be isomorphic, because essentially the groups are the same, so the algebra will be the same. But it's not clear. It's not clear why it should be the other way around. Like if you have that the algebras are the same, why the groups should be the same? So this is the case for the L1 algebra of the group, and essentially what this is saying is, well, you start here, you have some information that is a group, and from there you obtain an algebra. This procedure that you're using doesn't lose any information of the group, because you can recover the group from here. So all of the information of the group is retained here, And this is not true, for example, if you work with the C-star algebra of the group. So let me write that. This is not true in the C-star context. Because, for example, you have that the C-star algebra associated to C4 is isomorphic to the C-star algebra associated to C2 plus C2, but obviously the groups are not isomorphic. So essentially, if you were if you, the machine that you have like two machines, that the two machines use as an input a group. One gives you the C-star algebra of the group, the other one gives you the L1 algebra of the group. The machine that gives you the L1 algebra of the group doesn't lose any information of the group, whereas the machine that gives you the C-star algebra of the group does lose information. So this is a reason to think, well, maybe here when you work with these L1 algebras, there is something different happening than in the C-star context. And the second one is a little more recent. Is due to the show Svensson and Tomiyama, the second present that I want to mention. And it's in this context, but only when working with the actions of the integers. They proved that for an action, and this is from 2013, I think. They proved that if you have an action of the integers on a compact Hausdorff space, then the action is free if and only if every closed ideal of the L1 cross product is self-adjoint. So here, free, I mean like in the usual notion of a free action of a group, like the stabilizer subgroup of every point is trivial. So what I'm saying here is, well, you can detect freeness of the action by looking at this cross product and checking if every closed ideal of this algebra is adjoint. I should think I didn't say, I should have said this algebra. I forgot to that. I should have told this. This algebra, when you take the completion with respect to the norm I mentioned earlier, what you get is a Banach algebra, and also you had an involution that I defined earlier. So actually, what you have is a Banach star algebra. Let me write that because I forgot. This is a Banach star algebra. So what do I mean for the ideal to be self-adjoint? Well, that if closed, it is closed under the involution, essentially. So why do I say that this is an interesting precedent? Because if you were trying to do the same for the C-star cross product, well, the action you started with may or may not be free. That depends on the action. But in the C-star cross product, as in every other C-star algebra, it's automatic that every closed ideal is self-adjoint. So this will always hold on the C-star cross product, whereas this may not. So essentially, here, if you were to look at the C-star cross product, you will not detect freeness of the action. This way, at least, you won't be able to detect it because this is always true, and this may or may not be true. And maybe you don't detect freeness at all. So here is another example of, well, when you, from the action, you go to this algebra, you are detecting something from the action, freeness in this case, that is not detected, or at least is not detected in the same way in the C-star cross product. So this is another precedent that I think that shows you that, well, something different is happening here than in the C-star cross product. So, well, are there any questions? No? Okay. So now I want to talk about this. I said what I want to do is a dictionary between dynamical properties of the action of G acting of X and analytic algebraic properties of this algebra. So essentially, something like this, what the show Spencer and Tomiyama did, like you have a dynamical property that is freeness of the action, and you see that it's equivalent to some analytic algebraic property, that's this one in this case, of the cross product. So essentially, what you're saying is, well, I can detect this dynamical property as this property of the cross product. So this, let me say something. This study of this kind of dictionary between dynamical properties and properties of this algebra was started by the Shewus, Benson, and Tomiyama, but for actions of the interest. And what we did is to try to generalize this to other groups, countable, infinite, discrete groups. So that's essentially what we try to do. So the first interesting property you are able to characterize, and the one that is once you have proved that, is a tool you can use to prove other equivalences, is that you can characterize topological freeness of the action as what's called the ideal intersection property. Intersection property of the algebra. The one of X here of the algebra. So let me define these properties. So definition, we say that the action is topologically free. Sorry, let me define something before. Given X in X, we define the stabilizer subgroup of X, subgroup of X as G sub X, that is basically the elements of the group, such that X is the point X is fixed under the action of S. So this is equal to X. So we say that the action is topologically free if the set of points of X that have trivial stabilizer is dense in X. So essentially, the action may not be free because you might have points that have a non-trivial stabilizer, but the ones that have trivial stabilizer are almost all of the points in a topological sense. That's what it is. So the other thing that I said, well, we're going to compare this topological freeness with the ideal intersection property. So let me say what that is. So the ideal intersection property in L1 of G acting on X holds if for every closed ideal of L1 of G acting on X, if the ideal is non-zero, if E is non-zero, then the intersection of E with C of X is also non-zero. So I recall C of X is contained on this algebra. We mentioned how it was like if you take a continuous function, you take the element here that in the identity of the group takes that value, and in every other element it takes value 0. So basically what we're saying here is, well, this property holds if you essentially can detect all of the closed ideals of this algebra by intersecting them with C of X. That's what this property means, right? So the theorem basically is that the action is topologically free if and only if the ideal intersection property holds. So here you have another entry on this dictionary, let's say, that says, well, topological freeness is equivalent to this other property. And this is particularly useful because I will not go into the details because I don't have, I want to say other things, I don't have that much time, but essentially, this is the property that allows you to relate the ideal structure of the algebra with the dynamics on the space. Because I will just say this, if you have this property, then let's say you take an ideal, you can go and you can intersect it with C of x. If the ideal is not zero, then you detect it on the via this intersection, supposing that assuming that the action is topological free, and you have that all of the ideals on C of x are essentially are basically the continuous function such that they vanish on a fixed closed set. So basically, to this intersection corresponds some closed the closed subset of x. And what you also have is that this ideal here comes from the intersection of ideal on the bigger algebra, then actually this set must also be invariant. D is closed and chain invariant. So basically, this is the machine that allows you to say, well, the ideal structure from an ideal, I can get a closed invariant set that essentially has to do with the dynamics. And once you have this, you can, for example, prove this. I will not do the proof, but you can also see that, for example, minimality of the action is equivalent to simplicity of the L1 cross product. So let me say let me say define the thing. So definition, the action is minimal if there are no proper closed and G invariant subsets of X. This is equivalent. Maybe sometimes this is defined as every point on the space has dense orbit is equivalent. And well, simplicity is that the simplicity of the algebra that it has no closed ideals, let's say in this case. So what is the theorem? You can prove quite easily. And I mean, what I want to say is that actually once you have proved this theorem, this one here is really easy to prove actually. The theorem is, well, if the action is topologically free, then the action is minimal if and only if L1 of G acting on X has no proper closed ideals. So basically, once if you assume topological freeness, then you have that minimality is equivalent to simplicity, and it makes sense because given this way that of relating ideals with invariant subsets, so what you would say is, well, suppose that if I have a G invariant proper subset, closed proper subset, then you can easily see how to obtain a proper ideal of the algebra. This is basically the elements of the algebra such that the component, the continuous function that is the component in every coordinate vanishes on that fixed set. So basically, if the action is not minimal, then the algebra is not simple. And the other way around would be like if you have a proper ideal, then you intersect it with C of X and you will obtain a proper subset, closest invariant subset. So that cannot happen. That's the idea, but it's a few lines for if you were to try to write it. So what are the properties you can prove? I will just write them, and then we continue with that. For example, you can prove that topological transitivity of the action is equivalent to some notion of, I think it's called primeness, but that might be wrong. I'm not sure. So let me write explicitly how that is. So topological transitivity means that for every pair of U and B of open, non-empty subsets of X, there exists some element of the group such that sigma S of U intersection B is non-empty. So essentially, what you have here is you have U somewhere over there, this is X, you have B somewhere over there. Well, then you can move U through the action of one element such that there is an intersection with B. So what is the theorem that holds here is, well, suppose that the action, again, you have to assume topological freeness of the action because that's the tool you have to relate the ideal structure with the dynamics. So assuming topological freeness of the action, the action is topologically transitive if and only if for every pair of closed non-zero ideals A and J of the algebra, you have that the intersection between A and J is non-zero. So you can think of it like, well, if in the dynamics the open set get all mixed through the action, then the ideals must also intersect. That's the idea. Well, the other thing you can see, I will not write it. There is a dynamical property called residual topological freeness. That it means basically it's stronger than the action being topological free. Is that the action is topological free, and also if you have any other closest invariant set, then if you restrict the action to that set, it is also topologically free. That is equivalent to what's called the ideal separation property. That means that if you have two ideals such that when you intersect them with C of X, you get the same, then the ideals must also be the same. Yeah, I want to write it because I have only 10 minutes left and I want to say other things, but you can also do it. So what I want to talk about now is about detecting freeness. That is kind of going back to this present that was proved by the share with Benson and Tomiyama that I think it is interesting. Detecting freeness of the action by looking at the one algebra. So the thing here is I want to try to prove. I had this. Let me write it again. This theorem that was from the share with Benson and Tomiyama that says, well, this action is free if and only if every closed ideal of this algebra is self-adjoint. So I would like to generalize this because this is the dynamical property that behaves different than in the C-star case. Because all of the results that I said before, they kind of work in the C-star cross product also. So it's not that different behavior than the one you would expect by looking only at the C-star case. But this one is more interesting. So you would like to generalize this, but the thing is, as it is written, you cannot generalize it because you have an example, a counterexample, that is, you have an action of C semi-direct product with C2 acting on the circle. The action is basically is not hard. It's basically I will just write it on the air because I don't have that much time. But the idea is, well, you need to define how you act with the integers, and you need to define how you act with C2. The integers basically act as an irrational rotation. Yeah, you rotate an irrational angle. And this one, what it does is, if you have an element here, then you take the symmetry with respect to the real axis. So basically, you send this element to this one, right? This action is minimal because it contains an irrational rotation, and the irrational rotation is minimal on the circle, and it's also topologically free because well, you can see it, but essentially what you have is that the points that have here by periodic, what I mean is the points that have a non-trivial stabilizer. The points that have non-trivial stabilizer are basically the things that can be written as, I think it was n theta plus m over 2. This is, let me check just in case, because I may be writing this wrong. No, it's fine. Such that n and m are integers, and theta here is the angle I'm rotating in with the rational angle I'm rotating. So these ones, the complement of these, that are the points that have trivial stabilizer, are dense. So the action is topologically free. So basically what you have here is, well, the action is topologically free. That topologically free. So as the action is topologically free and minimal, the algebra is simple. So the only ideals you have are the whole algebra and the zero. So trivially, every closed ideal is self-adjoint. So this holds, but the action is not free because you have points that have non-trivial stabilizer, right? So this means that this statement, as it is, doesn't work. You have to do something. And the thing is, if you look at the proof that they gave in their paper, essentially the thing is, for doing one direction, they use that the action is not free in the sense that I have described. And for the other, they use that for actions of the integers, not being free is equivalent to having a finite orbit, something that is not true in general. So you cannot do exactly the same thing. And there are other details that are kind of problematic to deal with if you have only a group. We don't know anything more about the group. But what you can prove is, well, let me say something, that this direction of the theorem, that if the action is free, then every closed ideal is self-adjoint. The proof they do essentially works the same. That does work all right. It's not problem. So you can check that. So this holds, Rob. If the action is free, then every closed ideal of the algebra is self-adjoint. And in order to do the other way, you have to impose some conditions of the group. And what you can manage to prove is thick. So suppose that she is abelian and torsion-free. Then if every closed ideal is self-adjoint, closed ideal of L1 of G acting on X is self-adjoint, then the action is free. So you have the reciprocal if you assume these things on the group, right? So this works. This works, and well, obviously, this example we gave it doesn't work because this group is not abelian, neither torsion free. So well, you have that. So I have only a few minutes left, so I want to say something at least about the last thing I want to talk about. That is this. What does it mean to the for the cross product to be isomorphic? So I want to talk about just briefly about what happens between the one cross products. So the idea is you want to do something like this one theorem I described before. That says something like if you have an isometric isomorphism, well, here is isometric isomorphism. If you have an isometric isomorphism between the algebra, what can you say about the actions? Would be in this case. So I will see the theorem, and I think I will stop because I don't have that much left. So the result, this is with Eusebio Gardella, is that if you have two actions, given two actions, she acting on X and H acting on Y, the L1 cross products, so L1, then let me repeat this, then L1 of she acting on X is isometrically isomorphic to the L1 cross product associated to H acting on Y if and only if she acting on X is conjugated to H acting on Y. So I will not write it because I don't have much time left, but for the actions to be conjugated means that there is an isomorphism between the groups and a homomorphism between the spaces, such that, well, I will write this, sorry, I changed opinion. So you have rho and isomorphism between the groups, and theta and homomorphism between the spaces, such that if you act with an element of the group over an element X of the space and you apply the homomorphism, what you get is rho of S acting on theta of X. So essentially, for actions to be conjugated, it's like they are the same from a dynamical topological dynamical standpoint. They are the same. So essentially, what you have here is kind of like an analogous to the one theorem I described before. So if you look at this algebra, you can recover the action up to conjugacy, and this is interesting, I think, because this is also different to what happened for the C star cross product or the LP operator algebra cross product, because it's not clear if you have two actions and you take the C star cross product, it's not clear what it means for the cross product to be isomorphic. But if you have an isomorphism that also preserves the canonical algebra continuum function, then that has to do with orbit equivalence. That is a weaker notion than conjugacy. So what you recover is less. And also you have to assume that the action is topologically free, something that here you don't have to assume. And for the LP operator algebra, something similar happens. It's a little more rigid because the isomorphism, an isomorphism between LP operator algebras automatically preserves this canonical commutative algebra. But again, what you recover is the continuous equivalence class of the action. And also you have to assume topological freeness of the action in order to make it work. And here you don't have to assume anything about the action. So I think I'm in time. It was 50 minutes. So I think I will stop here. Thank you.
Okay, thank you. Thank you very much. So, well, first of all, I'm going to ask you, so would you slide the slides down? Like I want to see, yeah, there, in the theorem.
Yeah.
Would you write you wrote then gx on x, and then you didn't write freely.
In which one? In this one?
The
Or in this
theorem.
one?
No, there. When it, you
I
didn't
might.
finish the sentence.
See, yeah, sorry. Sorry, yeah. Then the action is free. Sorry.
Yeah. So,
Yeah, exactly.
yeah.
Thank you.
Would you make it full screen again?
Yeah.
Now, in the rigidity theorem, you do not ask that the involution be preserved. Is this
No,
automatic?
it's automatic. It's automatic,
Okay.
yeah. Essentially,
Okay.
what you prove is that if you have an isomorphism between L1 of G acting on X and
Because it
L1
must
of
send
G.
the involution on G is G inverse. And
Yeah, essentially you
so,
have this, that if you want to map this element, what you get is F precomposed with the inverse of the homomorphism, delta progress. It must have this formula.
mhm. Okay, and yeah. So a general question is, have you considered as a special case? I mean, so the space on which you act, your standing hypothesis is that it is Hausdorff and compact, right?
Yeah.
Do you get better properties or something if you additionally assume that X is totally disconnected, or more or even more specifically, if so, suppose I take what is called a shift space. So I take a bilateral shift space. So I take a graph E without sources or sinks, and look at the space of all by infinite paths on the graph. So, and then I take the shift, which gives me an action of Z.
Yeah.
So, in that particular case, do you get any? I mean, do you recover known results for graph algebras or something like that?
I don't know, actually. I have not think about that. If this result of graph algebra, you can somehow write it as an dynamical property of the shift, then in some sense you should be able to recover, because what this last theorem tells you is that all of the information on the dynamics should be somehow encoded on the algebra. But to be honest, I don't know. I have not think about that.
Okay, and the last question is whether what happens, for example, with the ideal intersection property. So it refers to when ideals of the completed L1 cross product are determined by the diagonals of algebra, the continuous functions on the space on which the group acts, right?
There is two properties. The ideal intersection property tells you that you detect ideals by intersecting effects, but it could happen that if you have two different ideals, when you intersect, you get the same. So you may not detect it. That is what's called the ideal separation property.
Okay.
And actually, that is equivalent to that last thing, the ideal separation property, is equivalent to the action being residually topologically free. That's something that I mentioned. I didn't write it, but I did mention it really fast, to be honest. That means, yeah.
Yeah, so the property I was referring to was, so if you slide back and we look at the theorem.
Yes.
That was
This one, I suppose.
not primeness noted before. I think it
No,
was one of the
sorry, it's
first properties.
the internet.
Yeah, and the ideal
There?
intersection property was that for an ideal to be non-zero, is the intersection with Cx have to be non-zero, right?
Yeah.
Now, you may ask whether this L1 cross product is a completion of the algebraic cross product, which is the algebra you described first. Right?
Yeah.
Uh, uh, is there a theorem that, under some circumstances, says that a non-zero ideal of the cross product, the completed cross product, must intersect the uncompleted cross product non-trivially?
Mm.
Or can there be, ideals that
Yeah, they do not intersect the.
because in principle this Tabaré
Uh,
is dense, but the closed ideal, I mean, well, it would
uh,
intersect at
yeah.
zero, right? But because I mean,
Uh,
in the I think in the graph algebra case, I think that the closed ideals, say the gauge invariant closed ideals of the sister algebra, are the same as those of the Levitt algebra, or the uncompleted ones. So so yeah.
yeah, I don't know. There is some properties like this stronger notion of the ideal intersection property that essentially the choice. I choose C of X. You could choose any subalgebra, like for example the incompleted cross product, like you say, and you can wonder if the property holds or not. In this setting, I don't know. In other
Mhm.
settings, I'm not entirely sure. I think that this has been studied. The sister cross product, the reduced sister cross product, you can see it as a competition of this L1 cross product.
Yeah.
Actually, you can see it as that, and you get the same. And
Mhm.
I think it has been studied when does the ideal intersection property between the sister cross product and the L1 cross product
Mhm.
holds.
Mhm.
That has been studied
Mhm.
by Hannes Thiel and Areosta, I think.
Mhm.
I don't know exactly the details, but there is something with that. If you were to ask about the uncompleted cross product,
Mhm.
that I don't know. Maybe there is something, but I'm not sure.
Okay. Okay, so that's all the questions I wanted to ask. Is there anyone in the audience who would like to ask something?
Yeah, maybe I have a question.
Yeah, sure,
Yeah.
sure.
Yeah, so for example, in your case, you characterize the minimality of these actions by the simplicity of the respective L1 algebra, right? But
Hmm.
there's this among the minimal actions, there's one that is the universal in the sense that it covers every other minimal action that you can come up with. Have you thought about
The one that
characterizing
is in
that?
the.
Huh?
You mean that the one that is in the counter set, like any minimal action of a compound house, I think, or metric, I don't remember, is a quotient of the minimal action of the counter set.
Hmm. Yeah. Well, I'm not sure if the counter set. But yeah, it's on those lines that you have this universal minimum action, which is universal in the sense that it covers
Mm.
every minimal action.
Okay, okay. No, no. To be honest, no, I have not think about it. I have in my mind that it exists, at least with the one I just described about counter sets. I know that there is some sort of result like that. Maybe what I said is it might be wrong. What I said, I'm not sure. Uh, but no, I have not think about that. And that might. Me interest. Yeah. What I say is it's not the same as you were saying, I think, because the action of the counter set depends on the action you are like lifting, but it's not universal for every minimal action. Maybe there's some sort of, I don't know.
Yeah, I think the counter one I think is
Maybe
universal among the metriceable ones, I guess.
yeah.
The
Maybe
metriceable
that.
ones I will be
No, to be honest, no, I didn't know the one you're describing. I didn't know actually the property, and no, to be honest, I had not think about that, but that might be interesting. Yeah.
Okay. And maybe another question if there's time left.
Yeah,
Yeah,
sure.
Prof, please.
For me,
Yeah.
have that.
Is there any hope to generalize this to non-discrete groups?
Uh, Maybe I'm really bad with non-discrete groups, so I don't think I'm the right person to do it. Maybe something can be done, but you lose many of the things because, for example, when the group is discrete, and the space is compact, then you have in this algebra you have both the group and both the space somehow encoded. For example, if the group is not discrete, then C of x is not contained on the cross product because C of x times the delta E is nothing. So it gets harder. Maybe there is something to do, but I don't know. I don't know that much about how you work with cross products when the group is not discrete.
Okay. Well,
But there
thanks.
is there is people that have been said the C-star cross product for non-discrete groups. Maybe there you can look for inspiration, probably. But yeah, as far as I know, for this I don't know if there is much. That's the.
Okay. Yeah, I was asking this because, for topical groups, there's an interest in studying these minimal actions,
Mm-hmm.
and especially
Yeah.
these ones that are universal, but,
Yeah. Indeed, that will be interesting, but I think it will be more harder than this.
Okay. Thanks.
No, thank you.
So are there any further questions? Otherwise, I will stop the recording here.